see this better. Well, thank you for the opportunity. Some of you I know, this is a talk, a version of a talk I gave at the philosophy department a year and a half ago or so. So if you were at that, if it's not that much different, you can feel free to leave. Otherwise, I will proceed. Anyway, as I indicated in the flyer that went around, when people ask, what do you teach, and I say philosophy and mathematics, they say, what? You know, what's the connection? Well, I want to make the case that there's a huge connection between these two fields, historically and even today. So, when I saw the flyer, Robert had asked me to send me a picture of myself for the flyer. And when I saw this, I thought, well, let's see, that old guy must be, again, that guy must be Robert. Minus the beard. This is a famous picture called The School of Athens. It was by Raphael. It's a fresco in the Vatican, and it really nicely brings together, serendipitously, because I didn't send him a picture, but it brings together the theme of my interest, which is mathematics, philosophy, and the fact that it's in the Vatican. Another interest of mine is religion and theology, given my current appointment as a director of the Kaufman Interfaith Institute. We'll come back to this image at the end as kind of a summary, because in a way it nicely summarizes what I want to say today. We're going to start actually with Pythagoras, a little before we because when I ask the students in 495 what's the most famous theorem, they always say the Pythagorean theorem. And this is a statue on the island of Samos where Pythagoras lived, and obviously it depicts the right triangle and his theorem, famous theorem. But Bertrand Russell said of Pythagoras that he was intellectually one of the most important men that ever lived, because the whole conception of an external world revealed to the intellect but not to the senses is derived from him. So Russell looks back to Pythagoras as the touch point for this issue between, can we have knowledge that is not necessarily from the senses, but is from our rational being. Plato is famous for having said the knowledge which geometry aims is the knowledge of the eternal and not of the perishing or the transient, from his Republic, Book 7. And then that brings us quickly to Euclid, who was a student in Plato's Academy, approximately 300 before the Common Era. And Euclid was, as I indicated, a student there. He went on to establish the School of Mathematics in Alexandria, wrote the Elements, and is probably most famous for today, especially for the axiomatic development of geometry. With 5 postulates, 5 common notions, he was able to prove 465 theorems. Now this is going to be old hat to the math people here, but this is what I had to tell the philosophers to remind them. He starts with common notions. Things equal the same thing or equal to each other. Equals added equals or equals. Subtracted or equal. Things which coincide are equal, and the whole is greater than the part. Nothing really profound, right? Pretty commonsensical kind of notions. Then he added to that postulates. 2 points determine a straight line. Again, pretty clear. Straight lines can be extended. A circle can be drawn given any center, point, and radius, and all right angles are equal to each other. Well, a fairly efficient set of axioms so far that he was able to develop so much out of these things. There was one kicker, of course, and that's the famous 5th postulate, which in Euclid's Elements reads, if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than 2 right angles. You know, the character of this postulate right from the very beginning is so different than the common notions and the others. And of course, it caused mathematicians for centuries a lot of problems. Why should something that is so rich in content and is far from intuitively obvious, whereas the others seem to be, why is that a postulate, and why can't we prove that? But anyway, that takes us down the story in its relationship to philosophy as well. Of course, that postulate was rewritten by Playfair in the 1700s, and the one that we usually learn now in high school geometry. Given a line and a point not on the line, there is one and only one line through the point parallel to the given line. Out of this, as I indicate, Euclid was able to prove 465 theorems, including the sum angles of a triangle equal to right angles, the Pythagorean theorem, congruent and similar triangles, prime numbers are infinite, volumes of cones, the cylinders, and spheres, and he ends his book 13 with a theorem about regular solids, which I want to discuss next. Regular solids are solids or polyhedra where each face is a regular polygon, all the sides are equal and the angles are equal, and each vertex of the polyhedron has the same number of faces and edges. He proved that there are exactly 5 such regular polyhedra, and they were called the Platonic solids. Now, in the math group, you probably don't need to see the proof, but for the philosophers, I did run through the proof real quickly. We'll start with what the 5 that were known in the time of Plato and Euclid: the tetrahedron, 4-sided, the cube or hexahedron, the octahedron, the dodecahedron, and the icosahedron with 20 sides. Now, Plato, they're called Platonic solids because Plato refers to these in his famous dialogue, the Timaeus. And the reason he refers to it is that way back at the time of Plato, there was this desire to combine science with mathematics, or to understand the scientific knowledge we have in mathematical terms. And that's still a very driving force in science today. If once you can get it, explain something in mathematical terms, you've explained it. Or as Newton famously said, I don't know what gravity is, but here's how it works. Here's the formula that works. So, and that's kind of started back in Plato's time. If you can reduce your science to your mathematics, then you've pretty much done the job that you're after. And the science of Plato's day was a periodic chart of 4 elements: fire, earth, air, and water. We think that's pretty primitive, but in his day there were people who were arguing that everything is water. And their argument was that, well, we see water in a solid form, ice, we see it in a liquid form, we see it in a gaseous form. So, it covers all the states of everything must be made out of this water. And there was other sort of intuitive reasons. When a fire burns, you see the air escaping in the smoke. You see the fire that's there. You see the crackling, which is the water that is leaving, and then what's left over the ashes are the earth. So wood, and when it's burned, you see it's made up of those 4 elements, and you can decompose it. Anyway, Plato said that the fire was actually little atoms of tetrahedra. And earth, because the tetrahedra, by the way, because they're very pointy, so fire breaks things up. The cube represented earth because it's nice and stable. Air was the octahedron. Water, because it flows and is almost round, was the icosahedron. And of course that left the dodecahedron, the 12-sided, and he says, well, that's the dome that covers the universe. Now, just to take this a little bit further with Plato's Timaeus, and this is a quote from the dialogue: to the earth, then, which is the most stable of the bodies and the most easily modeled of them, may be assigned the form of the cube, and the remaining forms to the other elements: to fire, pyramid; to air, the octahedron; to water, the icosahedron, according to their degrees of lightness or heaviness or powers of penetration. The single particles of any of the elements are not seen by reason of their smallness. Well, you got that right. We don't see atoms very well. They only become visible when collected. The ratios of their motions, numbers, and other properties are ordered by the God who harmonizes them as far as necessity permitted. And there's a 5th figure, which is made out of the 12 pentagons, the dodecahedron. This God used as a model for the 12-fold division of the zodiac. Now, he didn't just lay this out, he also did what we would call today in chemistry, he balanced equations. For example, water, which remember is the icosahedron, has 20 faces. If you break it up, you get fire, which is the tetrahedron, 4 faces, plus 2 airs, which are the octahedron. So 2 times 8 plus 4 is your 20. So there's got the equation balance there. A volume of air divided in 2 becomes 2 fire. 2.5 parts of air condensed into 1 of water. An equation like that, we would like to make those whole numbers, so we would probably say 5 air, which is 40 faces, equal 2 waters, which is also 40 faces. So he had a whole concept in his science of balancing equations, as we do now in chemistry class. The point I want to make is that the science in Plato's day has been replaced many, many times over, and we kind of all smile when we hear about Plato's science. But Euclid's proof is still valid today. the mathematics that was proven during the Greek era is still good mathematics today. Mathematics is the best and most certain description of reality. That's the idea that people have for over 2 millennia. Again, this is for the philosophers, but I'll just quickly run through it. So we can just quickly see how Euclid's proof was written. He says if we're going to look at polyhedra made out of triangles, and we're going to argue there's only 5, let's look at what we're dealing with. He starts with, and I'm putting this, of course, in degrees instead of right triangles, but we start with 360 degrees in a circle and 180 degrees in a right triangle. And so in an equilateral triangle, which we're going to build our polyhedra out, each angle would be 60 degrees. The tetrahedron has 3 vertices on each, 3 faces on each vertex, and the sum of the angles then would be 180 degrees. He says that's consistent. We know that works. And the octahedron has 4 faces on each of the vertices, and the sum of those angles are 240. And the icosahedron has 5 triangles on each, and you take 5 times 60 degrees, and you see we get 300 degrees. That's still possible. But if we try to make something out of 6 triangles, the sum of them at the vertex would be 360, and so it would be flat. They could not form a 3-dimensional. And then he does the same thing with the cube. Of course, now we're dealing with 90 degrees, and the sum of 3 of them at each vertex would be 270. But if we tried to make one out of 4 squares, it would be 360, and again, our figure would be flat and would not have 3 dimensions. Then we go on to the dodecahedron, which is made up of pentagons, and each vertex has 3 pentagons. And the angle of each pentagon, if you don't know offhand, we just break it into 3 triangles and add those up and divide by 5, and we see that each angle is going to have 108 degrees. And when we have 3 of those, we end up with 324 degrees, which is still possible. But if we tried to put 4 together, it would exceed 360, so it would not be able to be a convex polyhedron. And then we go on and say, what about hexagons? Hexagons can be thought of as equilateral triangles. I mean, you can break that up in equilateral triangles. So each of those angles would be 120, and of course 3 of those give us 360 again. And anything larger than that cannot be a building block for a polyhedron because it would have too many degrees at the vertex. Anyway, that's just a real quick run of Euclid's proof, and that concept still holds today. That's still good after 2,000 some years. So they knew at the time there were 5. And the issue for Euclid was to prove that there can't be any more. His proof is still valid, Plato's science is not. And the impact that this had on mathematics and our knowledge in general is this idea that mathematics gives us certain knowledge. It's not knowledge that will change. Once we've proven something, we now enter the realm of what Plato would call the eternal. We have eternal truths that are not subject to change. There can be no better description of reality than what mathematics provides. Mathematics was seen as the perfect science. It was seen as a science, and at the time, mathematics was not, as we see it today, a model building, but it was an actual description of reality. It was the queen of the sciences. This continued on into the Renaissance. Galileo said the great book of nature can be read only by those who know the language in which it is written, and this language is mathematics. Kepler said the laws of nature are but the mathematical thoughts of God. Kepler, by the way, was still intrigued with these Platonic solids to the point that his first attempt to provide the laws for the orbits of the planets around the sun, he attempted to circumscribe around the Platonic solids these spheres, and then around that one another Platonic solid, and he found that the ratios between them was fairly intriguingly close to what the empirical measurements were, but it didn't work very well. Fortunately, he gave up on it. What's interesting to me is that here, 1,500 years later, more than that, they were still trying to make sense out of the Platonic solids as a principle of explanation for science, for what we were discovering. Even as Plato did, Kepler was trying to do it. He did finally give that up and said, it's not circles. Back, the Greeks thought that the circle was the perfect figure, and so the circle must be the way the orbits would go. He gives up the circles and says, let's go for ellipses instead, with the sun at one of the foci, and he gives up constant speed. Another principle of the Greek idea was not only the perfect figures, but also constant speed. And he gives that up and says speed is not constant. The planets go faster as they get closer to the sun. What is constant is the area that is mapped out in a given time frame. And you think about this conceptually, why in the world would area of a two-dimensional ellipse have anything to do with the speed of planets going around? I mean, the conceptual break that he did with his laws of planetary motion is profound when you think of the 1,000 years plus of Greek ideas of constant speed and constant radius, where the circle is the perfect figure. It's the area that's constant. Descartes goes on as a philosopher. We know him as a mathematician, but the philosophers like to claim him too. And what's interesting about the connection here is that for Descartes, mathematics was the model for the best kind of knowledge. Descartes was living at the time of Renaissance, Reformation in Europe. A lot of things that were believed to be eternally true were kind of falling apart. He traveled around Europe and elsewhere to try to broaden his education. Finally realized that there was really nothing he could put his stakes down for that would be certain, except mathematics. He found mathematics was the model. In his discourse on methods, which, by the way, the appendix was called La Geometrie, the analytic geometry is actually just an appendix to his philosophical work. He says it's only the mathematicians who've been able to find some proofs, that is to say, some certain and evident reasons. I was especially delighted with mathematics on the account of their certitude and the evidence of their reasonings. And so when he set forth his 4 points on method, these are what they are, and as mathematicians we will recognize them. Not to accept anything as true which did not clearly known to be true. There's Euclid's basic common notions and postulates. Divide each difficulty into as many parts as possible. In an orderly way, begin with the simplest objects, gradually climb right up to the knowledge of the most complex. And fourth, make my calculations throughout so complete and my review so general that I would be confident of not omitting everything. A good set of guidelines for math students. Those long chains of reasoning, all simple and easy, which geometries have habitually used to reach their most difficult proofs, gave me occasion to imagine to myself that everything which could fall under human knowledge would follow in the same way. So Descartes as his method for philosophy. Even Hume, the great skeptic, who questioned everything, including causality and everything else, said, though there never were a circle or a triangle in nature, at least understood that these were abstract things, that we never can see a circle because it's two-dimensional. Anyway, the truths demonstrated by Euclid would forever retain their certainty and evidence. So even a great skeptic like Hume sees mathematics as that certain truth. Famous mathematician Kant said, all properly mathematical judgments are synthetic a priori. For Kant, if you do a little review of your introduction to philosophy, he divided things which were analytic and synthetic. And analytic were things like mathematical statements, or all bachelors are married, things that are true by the very nature of the words. Synthetic are things that are true about nature. They're not true just because of the way the words, the meanings of the words. And a priori, those things that we know before we've experimented. A posteriori are things that we learn from experience. And Kant famously said that mathematics is synthetic. It's not true just because of the meaning of the words, because there's nothing in all triangles have 180 degrees. There's nothing in the meaning of those words that would make it true. It is something that's true apart from the meaning, and yet it is not and yet it is not something that we find through measurement and evidence. We don't go out and measure triangles and then come to that conclusion. So his whole idea was that mathematics is synthetic and a priori, and that was an important part of his philosophy. In every specific natural science, there can only be found so much science proper as there is mathematics presented in it. Now, some of this is still true in science today. You know, people still, when you've got it down in the mathematics, you've pretty well got it done. The science of mathematics presents the most brilliant example of the extension of the sphere of pure reason without the aid of experience. And it's this debate through the history of philosophy between, does our knowledge all come through the senses, the empirical senses, what we can measure and experiment on, or is there knowledge that comes through reason that is not dependent on the senses? And this is you could describe the whole history of philosophy as a debate between these two. And mathematics plays that pivotal role always in the middle of that debate. Is mathematics empirical? We say no, it's logical. And does that mean, therefore, is that an argument in case of the rationalists? And the rationalists would argue, of course, as did Kant and Descartes and many others. And the empiricists would say, well, you know, there's other ways of looking at it. They have to account for mathematics, which is sometimes a tough job. How does mathematics function if everything has to be empirical? Anyway, well, I'll come back to the summary a little bit later, but it's really clear here in Kant and some of these others during this time period. Of course, the thing that really changed the whole world happened after Kant and Descartes and the early scientists, and that is the development of non-Euclidean geometry. Going back to the 5 postulates of Euclid, we see that 5th postulate on parallel, given a line and a point, not on the line, there's only one line through the point parallel to the given line. That was the one that had been questioned in many attempts throughout history to explain or to prove that based on the other axioms, or to take other axioms and prove this. For example, if one of your axioms is that all triangles, angles add up to 2 right angles. If you use that as an axiom, you can prove the parallel postulate. So there were lots of alternatives to the parallel postulate, but nobody could get by with just using the 4 postulates and prove this. But anyway, so that then became the question, and I won't go into all of the historical details as to how that came about with the work of Sackler and others. But the big 3 for the first non-Euclidean geometry were Gauss in Germany, Bolia in Hungary, and Lobachevsky in Russia, all working about the same time. Father Wolfgang said, "For God's sake, please give it up. Fear it no less than sensual passion, because it too may take up all your time and deprive you of your health, peace of mind, and happiness in life." Another little historical footnote here is that Wolfgang Bolia sent to Gauss his son's work, and Gauss said, I would like to praise it, but if I did, I'd only be praising myself, because I had actually worked that out years ago. What an injection letter. Anyway, then Riemann came up with the alternative. If you assume there's more than one parallel line, and you can get a consistent geometry, what if you assume there are no parallel lines? And of course, as you all know, in the Lobachevskian or Bolia non-Euclidean geometry, triangles have less than 180 degrees, and in Riemannian geometry, which is modeled by the sphere, triangles have more than 180 degrees. Now, Morris Klein, in his Mathematics in Western Culture, his big, huge history book, says, the importance of non-Euclidean geometry in the general history of thought cannot be exaggerated. Like Copernicus' heliocentric theory, Newton's law of gravitation, and Darwin's theory of evolution, non-Euclidean geometry has radically affected science, philosophy, and religion. It is fair to say that no more cataclysmic event has ever taken place in the history of all thought. In the math community, we know that non-Euclidean geometry was a very creative point at which a whole lot of new kinds of mathematics was developed. And we celebrate that. But Klein is arguing that it was such a shock, it was to mathematics. There were famous mathematicians that refused to even consider the non-Euclidean geometry. But he's saying that it also affected science and philosophy and religion. And the big thing here is, why did it have that huge effect? Because for 2,000 years there was this concept of eternal truth. And if you question whether there's eternal truth, just go check with your local mathematician and he'll explain it to you. Here's the eternal truth, and now that's clear. Okay, now let's go on. So when you have more than one geometry, and you no longer can claim that Euclidean geometry is the actual description of reality, not just a consistent system or a model, but it is the actual description of reality. If you can no longer claim that, then what can you claim? Where is absolute truth? What do we do with this geometry as the knowledge of the eternal? What happens to that? And the influence of that over 2,000 years was profound, and Klein recognizes that. It led to a rethinking of mathematics. The non-Euclidean geometry took place during the 19th century, and at the end of the 19th century were the great foundations of mathematics debates, and that's a whole lecture in itself, so I won't go through the details, except just to highlight who some of the major thinkers were. Logicism was developed by Bertrand Russell, intuitionism by Brouwer, and formalism by David Hilbert. If we want to talk about those, we can, but like I said, that's a whole other lecture. But I want to jump down to Bertrand Russell, because my talk is from Plato to Russell, and in particular, the subtitle I said that this is the 100th anniversary of the publication of the second volume of his famous Principia Mathematica. When I did this for the philosophy department, it was the 100th anniversary of the volume 1 of the Principia Mathematica. The timing's have been fine here. Anyway, Bertrand Russell, I want to tell his story, but I'm going to shift gears a little bit and move into a comic book form. It's nice to get a little change of pace. And if you're not familiar with this book called Logicomics, it's a really fun book that tells the whole story of Russell and Whitehead and the whole development and some of the problems that developed that. I'll give you a little excerpt from that in comic form. Here's Bertrand Russell's first wife saying, "Oh, Master Bertie is also displeased with philosophy. At least mathematicians try not to contradict one another. Not so philosophers. They are all great and all in total disagreement. They call this trash philosophy. I want to find my way to reality, man. I want a method to acquire certain knowledge." See that goal? That was there from Plato, Euclid on, and it's still with Bertrand Russell. He wants certain knowledge. If we unite the healthy parts of mathematics and the conceptual sophistication of the new logic, we can launch a powerful attack. He really wanted to build a foundation, not only for mathematics, but for philosophy, for knowledge in general. Well, he's sitting in on Alfred North Whitehead's class, and Whitehead says, to achieve any kind of certainty in mathematics, we must re-examine its basic assumptions. We must begin at the beginning. And Bertie sits back there, here. So he meets with Whitehead and says, sure, it's come a certain way since Aristotle, but is it strong enough to deal with mathematics? And Whitehead says, let's join forces. And Whitehead was famous for his book on universal algebra. And so Russell says, you mean write a second volume of universal algebra? He says, no, write together a brand new book. So they work on what becomes Principia Mathematica, which is kind of an interesting bit of overconfidence, maybe. Principia Mathematica was what the great Newtonian book was, and they decided to call theirs the same thing. And Russell gets excited. Whitehead, I've got it this time. I've finally done with the damn thing. And he says, really? You're done? What is it? It's proven. 1 plus 1 equals 2. On page 362, it says, and therefore, 1 plus 1 equals 2. And the kid says, I don't get it from you. Why 362 pages? Let me play, old chap. So it was such an enormous rethinking of logic and symbolic logic and the whole basis that it took that long for him to prove that 1 plus 1 equals 2. Russell then starts, as things develop, he starts losing confidence in his own program and says, to understand my predicament, remember that my profound underlying aim had never changed, to acquire certain knowledge about the world. Same idea. Somehow mathematics should give us information about the world. Knowledge which should only come from science. But science depended upon mathematics, which was a total mess, plagued by unproved assumptions and circular definitions. To repair it, a powerful logic was needed, but there wasn't one, and so we came to an impasse. He finally said, mathematics is a subject where we don't know what we're talking about, or whether what we're saying is true. And this was actually an insight that is important for all of mathematics, because Euclid tried, one of the problems with Euclid's Elements is that he tries to define everything. He defines a point as location without extension. That helps. A line is length without breadth. And as we often point out to our students, if you try to define everything, you get into circular reasoning. One example I like, I think it's Oxford Dictionary, that defines a dog as a quadruped of the genus Cana. You end up using more complicated words to describe simple words, and even if you have simpler words, if you look up the meaning of those, it'll eventually cycle around. So definitions aren't necessarily circular, and Russell recognized that. He also recognized that our axioms are not always intuitively true. They are beginning points. So we can't prove the axioms, and we can't ultimately define. So we don't know what we're talking about, and know whether what we're saying is true. In his Portraits from Memory, his autobiography, he says, I wanted certainty, again this key, certainty, in the kind of way in which people own religious faith. I thought that certainty is more likely to be found in mathematics than elsewhere. After some 20 years of arduous toil, I came to the conclusion that there was nothing more that I could do in the way of making mathematical knowledge indubitable. The splendid certainty which I had always hoped for in mathematics was lost in a bewildering maze. So, 100 years ago, they published their 3-volume Principia Mathematica. He died at 98 in 1970, 42 years ago now, approximately. But the question of mathematics in reality, and the search that Russell, along with Euclid, Descartes, and many others, is still a question that we often ponder. Does mathematics describe reality? Is mathematics just a game, as some of the formalists were? Is mathematics meaningless? Are mathematical objects real? Are numbers real? Are points and lines real? Reality is one of the issues philosophers deal with. It's called ontology. Ontology is what is real, what is true. And so these are questions that a philosopher would want to pose to the mathematician. And if mathematics is not real, we have this much certainty about mathematics, and everything else is less certain, and mathematics isn't real. What's going on here? Questions of, is mathematics discovered or invented? Question of certainty in mathematics. Realism. The status of logicism, formalism, intuition. These are kind of the questions we deal with in philosophy of mathematics. And then finally, the question of structural realism. In the last 20 years or so, there's been a new movement in the philosophy of mathematics called structural realism. And that's another whole talk, which I don't have time to do today, but it's one that I have presented at some international meetings. And it's a very intriguing way of making sense out of this whole question of whether mathematics is real. And it really comes back to the picture that Robert picked for the notice. And this is, like I said, from Raphael's famous The School of Athens. And it's a good way to summarize the part of the story I want to say. The person on the left is supposed to be Plato, and notice that he is pointing upward. He is pointing to the rational truth, to the certainty that transcends our experience. And Aristotle is saying, no, it's here on earth. It's empiricism. It's what we can see. It's what we can touch. It's what we can feel. It's what we can hear. It's what we can measure. It comes from the sciences. And Plato says, no, there is knowledge that comes from outside. It comes through our reasoning. And so this is a summary, in a way, of what the role of mathematics has been in the history of philosophy, is this tension between, can there be knowledge that is not empirical? Is there knowledge, even better knowledge, that comes through our reasoning and through our rationality, that is not subject to empiricism and to what our senses tell us? But since I have a little bit of time, I guess I went to race through this pretty fast, realizing I was under time constraint. I'm going to take the opportunity to do a personal postscript. And I want to talk about three famous philosophers: Wittgenstein, Russell, and Karl Popper. And Russell, of course, we've talked about, became not only a famous mathematician, but a famous philosopher. Karl Popper was one of the famous philosophers of science, and Wittgenstein was the philosopher who, in many ways, caused the revolution towards analytic philosophy, and then a whole new way of looking at philosophy in his philosophical investigations. Probably, most people would argue, is perhaps the most influential philosopher of the 20th century. A lot of interesting stories about Wittgenstein, too. But the story I want to tell is when Popper was invited to the Cambridge University Moral Sciences Club. This is the club that the greats that belonged to Russell, Whitehead, Lotz, Wittgenstein. This was the sort of the elite club in Cambridge, and you had to be nominated to be and approved to be a member of the club. In October 1946, Karl Popper was invited for the first time. He was not a member, but he was invited as an outside lecturer to give a talk. Are there philosophical problems? Wittgenstein was famous for saying there really aren't any philosophical problems. It's just problems of language. We confuse ourselves with the way in which we talk about things. We talk about, I have keys in my pocket, therefore I have ideas in my head. In this, because the grammar is similar, we think that ideas are things like keys. If they're in your mind, then it's like keys in your pocket. And he says, his approach in analytic philosophy was to analyze things from a grammar and understand why they weren't really philosophical problems. And so Popper, on the other hand, as a philosopher of science, was committed to the idea that science does, in fact, describe reality, and there's a methodology for it. Falsification was the key term that Popper used. And he wanted to argue that there are philosophical problems. This whole story is recorded in a book that was published about 10 years ago called Wittgenstein's Poker. Because the seminar took place in Brathwaite, another famous philosopher, in his library in Cambridge. If you've ever been there, the faculty, once you make professor, it's pretty nice. You have an office, you have your own adjoining library with a fireplace to keep warm, and so the seminar was actually taking place in Brathwaite's library, and at one point in the debate, in the discussion after Popper made his claim, Wittgenstein got very, very agitated and argued against Popper, and said finally, and to make his point, he grabbed the poker from the fireplace and was waving it, according to the. And by the way, this story is really fascinating because there's about 8 different versions of what happened, depending on if you're a pro-Popperian or a pro-Wittgensteinian, as to who did what and what was exactly said. But they try to, unpack the whole thing. And finally, Wittgenstein says, "Give me an example of a moral truth." And Popper said, "One shouldn't threaten a guest speaker with a poker." Anyway, this was what happened. Now, in Brathwaite's library, there was a set of the Principia Mathematica, the 3 volumes, and I happen to have the 3 volumes of the Principia Mathematica. If you want to come up and take a look at it afterwards, I have even put a little sticky on page 362 where it says, "From this proposition it will follow, when arithmetical addition has been defined, that 1 + 1 = 2. But the other interesting part of this is that if you look on the front page, this was R.B. Brathwaite's personal copy of the Principia Mathematica. And when I left the dean's office in 2004, was it, the faculty, some of you were still here, collected some funds and bought me a bunch of philosophy books because I was moving into my faculty role. And one of the treasured things were the 3 volumes of Principia Mathematica. There aren't very many original editions of this around, I don't think, anymore. And to not only have one, thanks to my faculty colleagues back then, but to have Brathwaite's when it was part of the story of Wittgenstein's Poker is kind of a special little personal thing for me. So anyway, for me, that kind of pulls together my own personal history as well as my exploration over the decades in philosophy and mathematics and how these things fit together. So I think with that, we're done. Any questions? Is that all you have to do?
Any questions for our speaker?
Yes. I'm just trying to think, it seems to us in this present day that philosophy and mathematics are further apart than they were 25 years ago. Is that because of the strength of science becoming stronger than along those lines of the last 25, 30 years?
Well, I mean, certainly the success of science has had a big impact. But I would argue that that's sort of a positive force on why we tend to see things scientifically rather than mathematically. But I would argue that the other part of it is the shift in the understanding of mathematics is no longer a science. It is not a description of the empirical reality. It is something else. And whether it's a game or whether it's meaningless or whether it's what it is, we still don't have a good handle on it. But very few people would argue that it is a description of empirical reality. It may be a description of another part of reality. If one argues that there is more to the universe than matter, and science is primarily looking at matter, but there are other things like structure, structural philosophy tends to do that, or like relationships, then patterns, and all these things are things that mathematicians also like to talk about. If you say that reality includes those kind of things, not just material things, then there may be a place for that. But it doesn't have the same role that it had. And I think that the case I would like to make is that really the turning point of that began as Morris Klein suggested with the development of Euclidean geometry. That's when the sort of the stranglehold on reality in mathematics is yes.
So there's a real push, and have been for quite a while, that in the teaching of, say, K-12 mathematics, that it's real life. Do you see that as part of the issue as well? And
It's real life?
yeah, that the question often becomes is, as you're teaching this particular lesson, how does it relate to real life?
Well, that's me. I mean, I might want to think about it a little bit more, but my first reaction would be that's a pedagogical question.
Mm-hmm.
And I think pedagogically, of course, we want to teach things that are relevant to real life. And so is mathematics relevant? Absolutely. In fact, if science is more dependent upon mathematics now than it's ever been. And so does mathematics inherit its reality via science?
Mm-hmm.
Maybe. That's one way you could argue the case. Or is science reach a dead end when it puts things in mathematical terms? And it finally says, we can't go any further because I have now put it in terms that are no longer empirical, that are rational. And that's as far as we can go. Science does not proceed, uses reason of course, but it doesn't proceed with an axiomatic base that is apart from empiricism. And I find it really interesting that people like Dawkins and others say that there is no reality other than what the scientists can discover. And yet the scientists use mathematics all the time. And they haven't discovered that through their empirical method, which is supposed to be the summa bonum of all knowledge. When they finally get to mathematics, that's as far as they can go, and they think they're done. They think, hey, we've got it, got our nailed. So anyway, your question is interesting, but I would tend to think of it more in pedagogical terms. Mm-hmm. That we want our students to relate to these things in real life terms. And I try to do it in college classes too, so I think that makes sense. Do I have time for my foundations lecture?
If there's no more questions, let's thank Professor Kinsey again.
If you're interested in the print copy or comments, I'll brought them along.